Good evening, everybody. Welcome to the Royal Astronomical Society of Toronto, Royal Astronomical Society of Canada. Oh, well, small little faux pas. Toronto Centre, and it's our speakers' night for the evening. My name is Paul Delaney. I am not Ralph Chow. He's a little bit smaller than I am, and I am your second vice president. We're waiting for Ralph, but we're going to start anyway. So, first off, any newcomers for us this evening who have made their way to us? Congratulations. There are two types of meetings. You're present at a speakers' night, and that happens monthly from September through till May inclusive. And then in between those nights, so every second week, we have what we call our recreational astronomy night, where you hear from the collection of our members, what they're up to, what they're hoping to do, to observe, and so on. So there are a total of 2 meeting nights per month. And then, of course, it's just the recreational astronomy nights that run through the summer. Okay, so without any further ado, seeing it is a speaker's night, we're going to move to our speaker for this evening. And as the title suggests, it's Chris Gainor. Chris heralds from the West. He picked up his PhD at the University of Alberta. He has actually authored 5 books over the years, has been a professor over at the University of Victoria as well as the Royal Military College. And not to mention the fact that he happens to be the President of the Royal Astronomical Society of Canada. So we're absolutely delighted to have Chris with us tonight. As I said, he is a historian of spaceflight and aeronautics. Tonight he's going to give us the real scoop on the Hubble Space Telescope. Chris.
I can use this. All right, well, I guess we'll adjust the sound a little bit, but thanks very much. I'm going to just say a couple of things with my president's hat on. It's really exciting for me to be here because this is the first time I've ever been to a Toronto Centre meeting. With all the years I've been in the RASC, and I realized that it was here in Toronto that it all started 150 years ago. And I did live in Toronto briefly, and I've been to a couple of Toronto Centre activities, but never a meeting. But I was here for a board meeting, which took place last weekend, and we're working on a lot of issues to try and bring the RASC into up to date. We're talking about freshening up the committees and talking about our publications and things like that. So I was glad to see that our meeting coincided with this meeting, and I was able to speak to you. So, you know, if you want to talk about any national issues, don't hesitate to call me after the meeting. But I'm going to tonight I'm going to be talking about the Hubble Space Telescope, and the reason why I know anything about it, beyond what a lot of you would know, is because a few years ago, the Hubble project decided that they needed a history of Hubble operations. And I've become a historian of technology, especially space technology. And so I bid for that contract, and so I've spent the last 3 or 4 years working on a history of Hubble operations. Now, there is actually quite an excellent book written about how Hubble was built. It's called The Space Telescope by Robert W. Smith, who's a good friend and kind of academic mentor of mine. And so my book picks up where Robert's book leaves off. Now, when I talk about the book, I'm afraid don't have one in stores yet, but it's still probably a couple of years from being published. But when it is published, I'm sure there'll be a fair bit of publicity about it, and hopefully I'll be able to come to Toronto and help vlog it. So anyway, So I'm going to just start in on this talk. I'll just get my position here and let's see. All right. So the Hubble Space Telescope is named after this fellow, Edwin P. Hubble, who made one of the most important astronomical breakthroughs, I think, and just a little under 100 years ago. And actually, the Hubble telescope is kind of building on Edwin Hubble's work. So what he discovered was basically that the universe is much bigger than our galaxy. 100 years ago, astronomers were arguing about whether the universe extended beyond our galaxy, the Milky Way. And a number of astronomers thought it was bigger than that, but Hubble found the proof. It's very difficult to actually figure out distances in the universe. It's on Earth. It's much simpler because, for example, if you see a truck a couple of miles away and you see its headlights, you know how big it is and how bright the lights are, and you can easily deduce how far away it is. But when you look up at stars or other objects in the universe, you don't know how big they are and you don't know how bright they are really, and so it's difficult to say how far away they are, and so the search has been on for, I guess, what you would call standard candles, stars with certain properties, and deduce and knowing that a certain star is a certain brightness, and one of those types of stars are called Cepheid variables, and so Hubble took an image of the Andromeda galaxy, our neighboring galaxy. Back then it was known as the Andromeda Nebula because we didn't know it was another galaxy like our own, and found a Cepheid variable in this series of images, and from that deduced that the Andromeda galaxy was about a million light years away. Actually, it's about twice that, but anyway, the fact that it was even as far as he thought at the time, basically was proof that Andromeda was a separate body from the Milky Way, and that thus the universe is much bigger than our galaxy. Another important figure in the history of Hubble was Lyman Spitzer, who was based at Princeton. And now, when people, and again, roughly 100 years ago, started talking seriously about space travel, the people did have the idea, well, let's put a telescope in space, but in 1946, Spitzer wrote kind of the first serious, detailed proposal for a telescope to make observations outside the Earth's atmosphere, and after he wrote that paper. He spent a lot of time promoting the idea of a space telescope, and he worked on it. And of course, he lived to see the Hubble Space Telescope actually fly, and he got to use it even after even after it was fixed. And another space telescope has been named in his honor, but he's the fellow who gets a lot of credit for Hubble. So the Space Telescope. I think most people in this audience know why we need a space telescope. We all know about the atmospheric turbulence and all the problems it creates for us, but of course, the optical wavelengths that we can see are very limited, and so with space telescopes such as Hubble and other ones like the Chandra X-ray telescope here, and I think that's Spitzer, right? And Compton and other telescopes. You can see a lot more of the spectrum, which gives you a lot more information about the makeup of the stars and their motion and various other things. So that's why we want a telescope like Hubble. And just as I was alluding to in the previous slide, we have a whole set of what we call great observatories. And Hubble was the first one, which was launched in 1990. Chandra, which observes in X-ray wavelengths, was launched in 1999, and it's still going. The Compton Gamma Ray Observatory is no longer operational, and the infrared, that's the Spitzer Space Telescope. It's still kind of going, but its operations are quite limited because it requires coolant, and I think it's out of them, and so it's near the end of the line. But this set of observatories have really broadened our nature or our knowledge of the universe. Now, these were not the first telescopes put into orbit. The first ones started going up in the 1960s, the orbiting astronomical observatories and the high energy observatories and things like that. But these are much bigger than the previous ones. So this is a schematic of Hubble, and it's a Ritchie-Chrétien reflector telescope. So it's got a big mirror. I think it's 94 inches across, and it's the main mirror is around here. The light comes down here into the mirror, and then onto the secondary mirror, and then down into the instruments, which are here. We have at any given time we have 4 instruments down here, which are roughly the size of phone booths. Hubble is about as big as a school bus, and then there's sort of the fine guidance sensors here, and plus there's 3 of them, and they're kind of like baby grand pianos, their shape. And then there's a 4th one, but it's not a fine guidance sensor. It's a camera generally. And you can see, and there, of course, there's control systems down here, and the solar arrays and communication systems. Now, Hubble doesn't use thrusters to point itself. It uses gyroscopes to determine which way it's pointing, and then it uses momentum wheels to change direction. And that system has to do a lot of work because it orbits the Earth about 16 or 17 times a day, and it's been doing that for 28 years now. So it's a lot of movement, and and it has very fine tolerances to do its observations. And in a given orbit, it's changing from bright light to darkness, and of course, often your target is eclipsed by the Earth, and so keeping this thing pointed is quite a major task. I'm just going to speak for a minute about Hubble's problems that you might have heard about recently. It has 6 gyroscopes, which it has on board to help keep it pointed. And the gyroscopes are going at, I think, roughly about, they go very rapidly. How many revolutions is it? 18,000, something like that? That's right. And there's kind of a moving part that's inside of the fluid in which the gyroscope revolves, and then there's wires that go to that that part in the center, and those wires corrode. And this is the problem with the gyroscopes. They corrode over time, and so generally the gyroscopes have only lasted a few years. We've had a few servicing missions. They put in a whole new set of gyroscopes in the last servicing mission now. And three of them were actually kind of improved from previous sets so that they wouldn't corrode so quickly. They were supposed to put in 5 of the new ones, but it's a long story. They weren't able to put in 2 of them. So they only got 3 of the new ones. So the 3 old type have now essentially failed. And then and the 3rd one just failed just a couple of weeks ago. They were concerned about one of the other ones. It wasn't spinning at the right speed. And they were afraid that they were going to have to operate on 2 or even 1 gyroscope. You want 3 for optimal operations. And just yesterday, the day before, NASA announced that the one they were concerned about seems to be operating at the correct speed again, which means they will be able to operate with 3 of them. They've had problems with a lot of the gyroscopes going offline before some of these servicing missions, so they have learned how to use it with only 1 gyroscope. But you do lose some capability with that. And especially, like, for example, solar system capability, because you not only have to worry about the motion of the telescope around the Earth and things like that, you also have to think about the motion of, say, if you're looking at Saturn or Mars or something like that. And apparently, when you factor that in, that's a bit too much for something operating on 1 or 2 gyroscopes. But anyway, with time, I expect that the other gyroscopes will eventually fail, and Hubble will stop operations, because it's been 9 years since the last servicing mission. But we'll talk about that a little bit. This here is a list of the various instruments that have been on board Hubble. So Hubble was launched in 1990, but today the Hubble is actually quite different in terms of its instruments from what it was when it was first launched. It has newer instruments, usually with much better and newer chips and more powerful instruments. I'm not going to go exhaustively through this list, but you notice that they have a number of different cameras with different purposes. And then, of course, the bread and butter work done with spectroscopy and the photometer and the similar work done. The sensors also act as a kind of a photometry instrument. And of course, you have CoStar, which was the instrument put on board to kind of correct Hubble's vision after the mirror problem. But let's and another thing is Hubble requires a lot of infrastructure on Earth, and also elsewhere in space. It beams its images up and receives them from Earth via the TDRS satellite system, the Tracking Data and Relay satellite system, which is used for various things. The shuttle communicated with it. The ISS uses TDRS so that they have coverage through most of the orbit, and even a lot of, shall we say, national security payloads in the US and other scientific payloads use TDRS. So you don't need those old-fashioned tracking stations on the ground. And the control of Hubble is done mainly through the NASA Goddard Space Center in Greenbelt, Maryland, which is in the suburbs of Washington, D.C. And Goddard controls a lot of NASA's scientific spacecraft. And about a half an hour up the road, depending on the traffic, of course, is the Space Telescope Science Institute at Johns Hopkins University in Baltimore. And that's where they have a large science staff that kind of direct the scientific operations for Hubble. And when they administer a number of things. For example, when somebody wants time on Hubble, there's a whole process you go through. And generally, the requests for time on Hubble are about 7 to 10 times the amount of time available on Hubble. And they have a process to sort out what are hopefully the best proposals for time on Hubble, and then they help the researchers do their work with Hubble and then send them the data. And the Institute also maintains the archive of Hubble data. This is a really important part of Hubble because it's actually taking a lot more data that can be dealt with immediately. And there's a whole bunch of data in the Hubble archive that can be that still has to be looked at and worked with. There's also a couple of other archives that have Hubble data. One is in Europe because the European Space Agency is involved in Hubble. And the third one is just down the road from where I live in Victoria, BC. The Canadian Astronomy Data Center has a full set of data from Hubble. Canada was not a formal part of the Hubble program, but a lot of Canadian astronomers were involved in it right from the word go. You know, my friends in Victoria, like John Hutchings and a few other people, played a key role in it, and a lot of Canadian astronomers have got time on Hubble or used Hubble data over the years. So its work actually goes around the world. You know, people from various other nations, of course, use Hubble as well. So Hubble, the work on Hubble got going, and to build it got going in 1977, and the hope was that it would be launched in the early 80s, and there was a number of delays, one of them being due to the loss of the Challenger shuttle. But finally, in 1990, it was launched, and people's expectations were very high, but people were in for a bit of a surprise when they started to work with the telescope. They discovered that there's problems with all the images, and the mirror, it turned out, and it took people a while, and I go into this in some detail in the book, to actually accept what had happened. The mirror had been ground to the wrong shape, and it was just out by, like a fraction of the width of a length of hair, and but still it was wrong, and you had what we call spherical aberration. And this was incredibly embarrassing. NASA was also suffering some other problems at the time. Now, the causes of it, the story is kind of complex, but essentially, when the mirror was ground in around 1981, almost 10 years before it was launched, the Hubble program was in a bit of a financial crunch and a bit of a management crunch, and somebody and there was an error introduced in a testing device. The device had to be set so that things were at a certain distance, but something didn't quite go the right way, and so somebody put a washer inside the testing device to make good that distance difference, a 30-cent washer. And so it was precisely ground to the wrong shape. And then they decide to save a few bucks by, even though they did do a set of tests on it, they normally would have done some other tests on it, which they decided not to do to save a few bucks. So they thought they had a good mirror. Now, when in June of 1990 they discovered it was wrong, there had to be a whole lot of work done to figure out what the exact shape of the mirror was. And it could have been worse if it was just like a haphazard problem. But because they were able to determine its exact shape, it made it easier to solve the problem. They also found the testing device, which had just been put aside in a warehouse somewhere and hadn't been touched since it had been used to make this erroneous mirror. So it also helped them in their investigative work. So NASA went to work and came up with two fixes for the problem. One of them was to take out the main camera and replace it with a new one. And fortunately, Ed Weiler, who was a kind of a top official in Hubble, had decided to already start work on a new camera. So and they could adjust the mirrors internal to the camera to compensate for the problem with this mirror. But and that fixed that camera. But then you had the other instruments, and a couple of people came up with the idea of creating an instrument called CoStar, which had little mirrors in it, sort of all comparable in size to the mirrors that dentists stick in your mouth, but they were ground to a special shape to compensate for the the problems in the mirror. And you might think that's straightforward. It's just, oh, it's just the reverse of what's in the mirror. It was much more complicated than that. It was some amazing work that was done. So they created these two instruments. They also had some other problems with Hubble. The original solar panels shook quite a bit when Hubble moved between the dark side and the light side of its orbit. And so they decided to replace the solar panels, and then there were just other things, you know, like, for example, some of the gyros started giving them problems. So in the fall of 1993, actually early in December of 1993, a shuttle servicing mission was set up, STS-61. And NASA had continued to have a lot of problems, and the astronauts went through an amazing amount of training for this mission, because it was felt that if this mission failed to repair Hubble, that might be the end of NASA. It was kind of that serious. But that mission went ahead, and it was a 100% success. Just because of a lot of hard work by a lot of people. And actually, it's interesting today, you know, in the early 90s, Hubble was kind of a byword for failure. And I don't know if anybody remembers seeing Naked Gun 2, but there's this you know, it's a Leslie Nielsen thing, and there was a scene in there where I think it's Frank Drebs, or the detective he played, is depressed because he's lost his girlfriend, and he goes into the losers bar and sits down, and the walls are lined with pictures of the Hindenburg blowing up, and the Challenger, and various things like that, and then there's the Hubble telescope. This was a terrible time to be working there, and then this mission worked out, and about a month after the mission, they were able to put this out and some other pictures. And the year after the mission was 1994, the year of the Great Comet Crash, and Hubble was able to get great images of the impacts on Jupiter. You know, mind you, we could see them quite well from the Earth, but Hubble was able to get some images, and so my friend Ray Villard, who's the PR guy at the Space Telescope Institute, said, you know, up until the summer of 1994, it was the troubled space telescope in every newspaper story or television story. And after the Shoemaker-Levy event, the word trouble disappeared, and lots of people today are oblivious to the fact that there was any problem with Hubble at all. So over the years, there were 5 servicing missions, and you can see in this slide some of the things that were changed out. Each of the servicing missions, they involved a lot of hard work developing the instruments. Also, a lot of politics amongst astronomers. Which instruments are we going to put up, and which instruments are going to come down? But a lot of work by astronauts and controllers to prepare for these missions, and so you can see them here, and I'm just going to talk a little bit about servicing mission 4, which was the last one, and one that's been an enormous success, I would say, because it's 9 years later, and Hubble is still, at least until a month ago, going strong. And if we'd have been 9 years out from any of the previous servicing missions, Hubble would be dead by now. I mean, part of it is that they put in better gyros in that mission, but that mission almost didn't happen. Shortly after servicing mission 3B, the Columbia accident happened, and that caused NASA to review the shuttle program and decide to bring it to an end, which they did in 2011. And the shuttle after that accident was basically dedicated to the space station program, just taking people to and from and taking pieces up to the space station. One reason for that was because if something went wrong, like what happened on the Columbia, the astronauts had kind of a safe harbor on board the space station. But when they went to Hubble, which is in quite a different orbit from the space station, there's no safe harbor. If you lose your tiles on a Hubble mission, it's going to be a bad day. And so the administrator of NASA, a year after that accident, Sean O'Keefe, decided there would be no further servicing mission, which meant that Hubble, was basically had a very limited time span ahead of it. But there was a lot of lobbying going on and a lot of work. And after O'Keefe stepped down for other reasons, the new administrator, Mike Griffin, restored that mission. But there were safety measures taken. For example, during the servicing mission 4, there was another shuttle on the pad ready to come up to effect a rescue if possible. While they were thinking about canceling that mission, there was also some thought given to a robotic rescue mission, which would have used the Dexter robot that was, of course, being built up here in Brampton by MDA. They did give that serious thought, but in the end they decided against it and they launched servicing mission 4. So Hubble its history is inextricable from the history of the Hubble or of the shuttle program, because it was in a low orbit where it could be serviced, and it was serviced regularly by the shuttle, which has given it its long lifespan. So one thing that sets Hubble apart from the satellites or the space telescopes that went before it was that it was actually in the business of making images. Most of, like the OAOs and things like that, were basically doing spectroscopy and getting that really important data, but it wasn't taking images that people, members of the public, liked. And Hubble throughout its career has been taking images. Now, I actually talk about this a lot in the book because, Hubble came along at the time when we were changing from using photographic film to CCDs, charged coupled devices, and it was kind of it always had CCDs when the images were processed, they have had a lot of influence on how images taken from other telescopes, including those done by amateurs, are processed. Hubble, and I think pretty well most telescopes, do not take color images. They take a set of images through different filters, and then the images are processed into color images, and because the the filters chosen are usually different from the, say, the standard ones that we would use on Earth. What is it? Because of Hubble's sort of wider set of wavelengths, the folks at the Space Telescope Institute developed what is called the Hubble palette, and they've written about it and shared that information with amateur astronomers who have often used some of these ideas in processing their own images. But of course, Hubble is about science, and I could go on for hours, and probably, well, Paul could probably go on a lot longer than I could, talking about some of Hubble's scientific discoveries. But a lot of these discoveries, incidentally, involve work with other telescopes. Some of them in space, some of them on Earth. We have to be kind of careful to make sure that not all the credit for a lot of these things goes to Hubble, but it certainly played a key role in a lot of this work. Prior to the launch of Hubble, I think most people were agreed that the universe was expanding, but probably the rate of expansion was slowing down. We discovered that the rate of expansion was actually accelerating, and it's still kind of a mystery. We say it's dark energy, but saying dark energy, in a sense, is kind of saying we still don't know a lot of why that has happened. So there's still a lot of work being done on the whys. A big reason Hubble was launched and was designed the way it is was to help determine the age and the size of the universe, and to look back into the early history of the universe. You know, Hubble is kind of a time machine, and right now the consensus, or maybe consensus is a bit strong, there is a bit of disagreement about it, but most people think it's about 13.8 billion years old, and of course that has implications for how big it is. Another important thing was the discovery of supermassive black holes in the centers of galaxies. You know, like, we can talk about black holes, but these are a whole different thing altogether. Much bigger, and of course an important part of the structure of galaxies. Now, it was telescopes on Earth that first started finding extrasolar planets, actually with a lot of help from Canadian astronomers who came up with some of the early ideas about how to suss them out. And of course, but once they started finding them, then the Hubble could be aimed at some of these stars with extrasolar planets to get some images of them, because the detection methods are kind of indirect methods, and Hubble has been looking at them and getting spectral data about their atmospheres and things like that. And of course, it's also been done some important work fairly close to home in our own solar system, observing the comet crashes and getting regular images of other planets. You know, an interesting thing was that at first it wasn't looking at Uranus or Neptune, but I was talking to Heidi Hamill about this, who is working on this quite a bit, and they had Hubble make some observations of the moons of those planets, but they thought, well, we know what the atmosphere looks like because Voyager flew by them in the 80s. Well, when they started looking at the portion of these Hubble images that showed the planets, they realized that the atmospheres had looked different from what they did when Voyager went by. So it's kind of done regular surveillance, shall we say, of those planets. It was also used to help direct the New Horizons spacecraft towards Pluto. Pluto is so small and far away that even when Hubble was aimed at it, you only got kind of very blurry image of Pluto. And there was a lot of concern that there might be, a lot of crap flying around Pluto that might affect the spacecraft. Hubble discovered a couple of extra moons around Pluto, but also helped give some assurance about New Horizons' trajectory. And, in New Year's, New Horizons is going to be looking at a Kuiper Belt object, and Hubble was brought in to help find that object because they were having trouble finding something for New Horizons to go through other means. So anyway, that's just kind of a quick look at that. So I'm not. I did talk about this a little earlier when I was talking about the work of Edwin Hubble, but you have all these methods to determine the size of the universe or distances of galaxies, the Cepheid variables I mentioned, and then certain types of supernovae, which are known to have certain brightnesses and sizes. And this is what was used for to measure the acceleration of the expansion of the universe. This arguably is the most important image that Hubble took. And what this is that this is a portion of space, very small, in Ursa Major, near the Big Dipper, that was thought to be empty. And a number of scientists suggested we should just aim Hubble at something like this and give it a lot of time. Like we're talking about, this exposure is days long. I forget what the exact number is, but they shot it over a couple of weeks, just looking in there. And a few prominent astronomers, people like John Bacall, suggested that this was a waste of time. This a massive amount of Hubble time looking in this empty space. John Williams, who was the second director of the Space Telescope Institute, the director of the Institute always has some time that he can just use as he likes. And so he decided this, and they got this amazing image, except for a couple of objects with the spikes there. Those are all galaxies. So even in so-called empty parts of the universe, as we see it from Earth, there's a lot going on. So this was the Hubble Deep Field, and a number of other deep field images have been taken with data also from other telescopes like Chandra and Spitzer and things like that. So that taught us a lot about the universe. And this is another one which looks even deeper to the universe, because you can see these kind of streaks here. Well, this is actually caused by gravitational lensing. The gravity of galaxies bending light that's coming from even farther out behind them. So this looks even deeper into the universe. Just briefly, I'm going to mention that amateurs were given time on Hubble originally. The first director, Riccardo Giacconi, decided, well, that the taxpayers help pay for this, so amateur astronomers should get some time. I've just pointed to him. So in 1986, this guide came out, and he worked out something with the Astronomical League, and amateurs were given time on Hubble. Now, this slide shows how much take-up there was. There was a lot in the first round, but then fewer and fewer people proposed. Why was that? Well, if you like bureaucracy, you're going to love applying for time on Hubble. It's a lot of work, and the professionals, a lot of them were taken aback by the amount of work they had to do to make a proposal for Hubble. So, and I think this kind of deterred a lot of the amateurs. And in the first round, not all of the proposals were carried out because of the mirror problem with Hubble. Interestingly, the one that wasn't carried out, it was a proposal from a woman named Anna Larson who lived near Seattle, and the fact that she was accepted and then got to go to the Space Telescope Institute and rub shoulders with these astronomers inspired her to get her PhD in astronomy at the University of Victoria, as fate would have it. And now she's an instructor in astronomy at the University of Washington in Seattle. But over time, fewer people applied, and so eventually Bob Williams, the second director, canceled the program. But there are other opportunities for amateurs to work with Hubble. I have here the kind of the gateway URL for the archive. If you can understand how to work with the data, it's all in the FITS format. Anybody here can go in and work with this data, and amateurs have taken Hubble data, images, and worked with them to create new images. At the bottom there, I actually put something in there where the folks at the Institute talk about how they process their images. And then there's a couple of citizen science projects that have gone on. The first one being the panchromatic Hubble Andromeda archive or something. I forget what it's. And what they did is they've taken a set of detailed images of much of the Andromeda galaxy, but you're also looking through Andromeda, and they wanted, the people working on this wanted to kind of pinpoint where objects behind Hubble were. So they enlisted citizen scientists to help them with that work through the Zooniverse website. And Zooniverse has a couple of other things going on that involve Hubble data. So there's still opportunities out there for amateurs. So now we're waiting for the James Webb Space Telescope, and this was the month, actually, for a long time that we were hoping the Webb telescope would be launched. But now it's been put off until 2020 sometime. It's quite a large telescope, much bigger than Hubble. It's operating mainly in the infrared. So it has kind of these gigantic sun shields as one of the measures it has to lower the temperature of the equipment so it can obtain infrared images. Another difference from Hubble is that Canada is involved in James Webb, and so we have some of our Canadian instruments on it and our own taxpayers' money. Now, JWST is being launched on top of an Ariane rocket from French Guiana, and it's not going to be 500 kilometers above the Earth like Hubble. It's going to be roughly 1.5 million kilometers away, about 4 times the distance of the Moon. So it has to work, and it has to unfold like a great big piece of origami. It's going to take some time to get to its proper location and then deploy, and it's going to be a nervous time. But it is going to be able to look back, further back into the history of the universe than Hubble or anything else has been able to do. So you can see kind of the evolution of that, and so James Webb is going to be kind of different because it is operating in the infrared. It won't have those kind of optical pictures that we've become used to from Hubble. The hope is that they get 2 years of joint operation with Hubble and JWST, that they can look at the same objects at different wavelengths. You know, I guess there's still a lot of hope that that will happen, but we can't have many more months like this one for Hubble or any further significant delays for JWST. So there was something else I was going to say, but I forgot what it is. But anyway, oh yes, Hubble makes a lot of observations in the ultraviolet, and when Hubble stops working, we're going to lose our capability of observing in the ultraviolet, and there's a lot of astronomers who do that, and I know there's proposals around to remedy that problem, but right now a lot of observations for Hubble are being done in the ultraviolet to kind of create a store of data for those astronomers to work with, and a lot of proposals for Hubble observations are being looked at with an eye for how they might benefit people working with JWST. JWST will not operate for the long period that Hubble has, because it can't be serviced, and has is using coolants which are unlimited supply and things like that. But I wanted to show this slide. This came out a couple of years ago. Now, people remember the famous Pillars of Creation image in 1995 that kind of helped put Hubble on the map as a success, but they repeated it. They had a better camera after the last servicing mission, so they took that image again, and as you know, this is kind of in the center of the Eagle Nebula, and then they did it the same thing in infrared wavelengths too. So I'm going to wrap up with kind of, well, what's the future for Hubble? We're seeing the gyros start to fail, and one day Hubble is going to cease operations, and its orbit is falling. Probably sometime in the 2030s, it's going to come back to Earth. Now, NASA is mandated to either bring Hubble in a controlled re-entry or move it into a higher orbit where it can't come back for a long time, which involves launching a small vehicle to dock with it and then move it either into a controlled re-entry or into a higher orbit. That vehicle has not yet been developed yet, by the way. So it's going to be interesting to see how that evolves, or if it evolves, and they just risk a situation like they had with Skylab. But that's still a few years away. The question comes up, well, why not bring Hubble back to Earth and put it in a museum, because it's been such a wonderful thing? Well, this slide here is actually dedicated to the proposition that a lot of Hubble is already back on Earth. A lot of its instruments, the ones that aren't there now, they've all been, the previous ones have been brought back. And this one here is actually the co-star that I talked about, the corrective lenses that were put up on the first servicing mission. And eventually, all the new instruments had the corrective lenses built in, so they didn't need this one, and they brought it back to Earth. So that's in the Smithsonian in Washington, D.C. You can go and see it. And then there's this one, which was the camera that was also put in on that first servicing mission, and it took a huge number of Hubble's most famous pictures, including the first version of the Pillars of Creation, and it took the deep field and all that. Now you're looking at it and you said, that doesn't look so much as like Hubble as it does like Al Capone's basement, or that shows that that's kind of the exterior part of that instrument, the shield, and it shows that it's sustained a number of meteoroid hits. Now that isn't what they did. They actually most of those hits were just kind of little pinpricks, and they sort of drilled around them to take them out to give them a closer look. So that isn't what it looked like when they brought it back, but that gives you an idea of how many hits it got up in orbit. Now, some of that would be micrometeoroids, as I mentioned. A lot of it would be orbital debris. But anyway, a lot of Hubble is already back on Earth. You can see the test article for Hubble, which has been kind of done up like Hubble. It's also in that museum. You can see the backup mirror that they created for Hubble, which actually was ground to the correct shape, unlike the first mirror. And I think there was a European instrument which is now on show in Germany somewhere. So a lot of Hubble is already back on Earth. So there's something here. I don't know. So that's the end of the talk, and I guess if there's time for questions, I'll be happy to take them.
There will be. There's always time for talks. Thank you very much, Chris. I certainly remember the launch very profoundly back there in 1990, and Hubble has certainly lived up to its billing as astronomy's discovery machine. 28 years and counting, and let's hope that it does survive the next 2 or 3 or 4 years until JWST gets around to being launched. Okay, so time for questions, and I'll hand the microphone off to our trusty runners.
Ron.
Thanks, Chris. Very interesting. Are there any plans in NASA, to your knowledge, about making a spacecraft that could repair instruments like Hubble that can't be reached by humans through shuttles or whatever? You think that James Webb, if it works in, 2020 it's going to be launched, whatever.
Yeah.
I think in 10 years it runs out of its coolant fluid, and you would think at least they could send somebody up there with more coolant fluid, because you get so much more astronomy if you could keep these things working. So is there any thought on a robotic repair system?
Officially, no. In fact, I was talking to Mike Griffin, who was the administrator of NASA, about 10 years ago, and he actually wanted to put a grapple fixture on JWST so that something could come up, and apparently it was taken off, and he was quite miffed about that. But there are these people. The story of how they put this servicing mission together. I've done it absolutely no justice in this talk, and I probably have to just dedicate a talk to that aspect of it, because there are these people at the Goddard Space Flight Center, with help from the folks at the Johnson Space Center in Houston, who worked on the methods of repairing Hubble. Like a lot of the repairs on Hubble, there were a lot of them that were planned and designed, changing out the instruments. That was all planned. But a lot of repairs were made on stuff that wasn't supposed to be serviced. They changed out the computers and the data recorders and various other things. The power system they changed out. That they weren't designed to be changed out. And there's a group of people at Goddard. They're headed by a guy named Frank Ceppolina, who is an amazing guy. He's actually in his 80s now and is officially retired, but I know that he still comes into work a lot. And they have an operation at Goddard called the Satellite Servicing Office, and which is working on stuff like that. And a lot of their work is classified, because sometimes people want to visit satellites for a variety of purposes. And I am sure that somebody has been thinking about, well, what happens if JWST has a problem? How much they've actually done to act on that, I don't know. I'm not privy to that. But NASA is developing a spacecraft called Orion, which is capable of flying to the vicinity of the moon or even beyond. In the Obama years, they're talking about sending Orion out to an asteroid, which I thought was a really neat mission, but most people didn't like it that much because they thought it would distract from going to Mars or something like that. So anyway, probably not, but I wouldn't say never on that. But was that kind of the same question? Yeah, and then I'll
Mine was similar. I was thinking, would someone like SpaceX or Blue Origin think about taking on the contract for keeping Hubble alive? I mean, sell it to them for $1 or something and keep it going with their own systems.
I haven't heard anything like that. Hubble, even its newer instruments, is kind of aged now, and it's I think it would be nice to see kind of a successor to Hubble. There's JWST, and then there's also telescope called W First, which is being developed, which has a much wider field of view than Hubble does, and the Trump administration wanted to axe W First, but that was reversed by Congress, so I hope that goes ahead. There's lots of ideas being advanced for new space telescopes, and it's probably best to focus on them. Even, Canadian astronomers are talking about a telescope called Castor, and which would also be kind of a wide field, but mainly, I think, ultraviolet telescope. So as long as kind of the fund support for these missions can be found or maintained anyway, there'll be some other things. So, and up near the top there, you had a question for me.
Hi, we have a few questions from online.
Okay.
The first is there accessible data that reflects non-astronomical benefits resulting from Hubble's photography? And it says maybe advances in digital photography, for example.
Well, I think it's sort of hard to kind of divide things out, but I think the development of Hubble did help with the advances in digital photography. And I know that there's been some work done with analytical tools from Hubble for things like, for example, mammography, diagnosis of breast cancer, and things like that. So there has been some other work like that done, because NASA is always trying to encourage these spin-offs, as they call them.
The next question is the news as of late about the gyroscope problem was a little bit disconcerting, but of course there are backups, and it seems that the operations will continue for some time. But is there a reasonable best guess timeline for how long Hubble can be kept running, and what's your sense of the lifespan?
Well, I think it's probably good for another 3 or 4 years, but we, in terms of the operation of the gyros, we are already way out there in kind of unknown territory. These things have lasted a lot longer than the previous sets of gyros, and they have more experience with them, so they're a bit better at nursing them along. So it's probably not wise to say anything beyond what I've just said.
Okay. And another question is, would you like to compare the Hubble optical system to some of the satellites that have been sent up to look down at the Earth?
Well, that's a really interesting question, because Hubble is basically a kissing cousin of the first generation of kind of digital data reconnaissance satellites that were sent up. For a long time, the first reconnaissance satellites used film, and then the film was thrown into literally what was called a bucket, and then dropped back into the Earth and picked up. And so Hubble was built by Lockheed Aerospace, and it was just down the hall from where they were building reconnaissance satellites, the KH-11 Cannon they are called. Now, but I've sort of had to tread carefully in talking about this because while the previous information on the previous satellites has now been declassified, these have not. Cannon and its successors are still classified, but there's a feeling that it's similar to them, but I think it is different in a number of ways. And just one comment: one of the things that contributed the mirror problem was because there was so much classified work going on in close proximity to Hubble. The Defense Department didn't want that many inspectors running around the plant, which kind of discouraged maybe taking a second look at the mirror. Okay. Yes. Well, of course, it's much smaller than those telescopes. It's only like 94 inches across, which is kind of small by those standards. But it's above the atmosphere, so it can look in the near infrared and in portions of the ultraviolet. So and there's also the question of adaptive optics, which allows telescopes on Earth to deal with the turbulence in the atmosphere. Well, they still can't deal with the restriction on the wavelengths you can see from the Earth. So it's yes, but those telescopes, because of their size, are going to be able to do some things that Hubble can't. Any more questions?
Are there any other spacecraft that can go to Hubble besides designed to, or
With humans on board?
Sorry?
With humans on board, or any? I mean, I
don't know. Yeah, probably both.
Yeah, well, there's in spite of all the work that's kind of been done on robotic telescopes that could visit or even intercept spacecraft, there's spacecraft that could probably come close to Hubble and perhaps even join up, but I don't think they could do anything. Right now the only spacecraft carrying humans is the Soyuz. Now we're going to have the Dragon going, and also the Boeing Starliner, and they could also go there, but they don't have this big cargo bay that the shuttle has, so there's not a hell of a lot you can do. Orion, none of those could go to the vicinity of JWST, but Orion could. But you would have to make special provision for the tools you have to take. Like a big part of the shuttle work is that they had that great big payload bay where they could kind of anchor Hubble, and then they had all this replacement equipment and the tools in there. That was a lot of work and kind of forgotten. So
nothing beats a good trunk, I guess, is what that amounts to.
That's right. That's right.
Okay, I'm sure Chris will stay for a little bit after the messages that are coming at us from our president and, of course, the meeting after the meeting. So if you would join me one more time in thanking Chris. Don't go. Ralph.
Well, it's always a pleasure to have a national president visit the Toronto Centre. It has been a while since we had a national president here to give us a talk. So I'm very pleased that you were able to come tonight and visit with us. And it was a very good talk, so thank you very much. And on behalf of everybody here, I'd like to just present this little token of our appreciation, Chris.
Thank you very much.
the end of some of our ongoing education programs. And so I'd like to take this opportunity this evening to acknowledge the role of our volunteers in delivering the education and public outreach program over the last few months. Of course, this is something that is part of our goals as an organization. It's stated in our letters patent to stimulate and promote interest in astronomy and to assist individuals and institutions in that end. And of course, that's what we've been doing over the last number of years, both here at the Science Center, up at the David Dunlap Observatory, and at other locations across the GTA. It's notable that our efforts this year will see us deliver programs to and content to about 15,000 members of the public. That's not bad for a group of about 60 volunteers. Too many names to read out, but again, just to give you an idea, this is just the group that we have listed as contributing to the programs here at the Science Center. So that's our monthly star parties, or rather solar observing parties, plus a number of star parties that are organized in the evenings at the Science Center out on the telescape. In addition to that, of course, we've got the DDO Outreach Committee headed up by Ravi Shankar. And again, we have a lot of people who have spent many a weekend and some weekday evenings up there providing support for our program there. Again, keeping the DDO functioning over the last few months. And in addition to that, we've had a number of other programs going on, school visits, NOVA, a large number of special interest events, including jamborees for both scouts and guides. And a new thing this year was cruising on the Chichimon ferry between Tobermory and Manitoulin Island for 4 nights to do talks on the Perseid meteor shower and to point out the meteors to the passengers. So we've got a lot of things going on, and again, lots of people to thank for contributing to these programs. So to back them up as well, we've got the back office, if you will, the CAO committee and the supervisor group there, scope production, our telescope loan program, the folks who are helping to stream this program to our viewers online, and of course the website committee that keeps our website operating, and your council that has to manage the finances and keep everything going. So a big thank you to all of these volunteers for their help in delivering our programs at the Toronto Centre. And so now we will just take a look then at the announcements, what's going on over the next couple of weeks before our next meeting. Want to just point out this new little logo here, which is for the Owen Sound Transportation Corporation. Because they were so pleased with our job at presenting the Perseid shower, meteor shower program, they've become a corporate sponsor. And in addition to that, they're interested in having us do some more presentations, not only for the Perseids, but other things in 2019. So we're just going to be starting to open the negotiations with them very, very shortly. So that's a bit of a change in our programming footprint. Okay, so 2 weeks from tonight, we have our next recreational astronomy night, Wednesday, November the 7th. And Paul Markov is still trying to root out a speaker for the Sky This Month that evening. Dennis Gray is confirmed to present on a digital occultation camera, and we do have one open slot for that evening as well. So if you'd like to come up and have a chance to talk about something of interest to you, or tell us about some observations you've made or anything else astronomical, please contact Paul about perhaps doing that presentation at that meeting. The next meeting after that, on the 28th of November, is a really big show. We have as our speaker, this is the second Charles Darrow lecture, which is sponsored by Sarah Seeger, our member who's at Massachusetts Institute of Technology. She has her friend, Professor Rainer Weiss, who is the 2017 Nobel Physics Laureate, to come here and give a talk on exploring the universe with gravitational waves, and that'll be part of the Science Center's Great Conversations series. And as the co-sponsors for the talk, Toronto Centre gets 200 free tickets. So you'll be getting a message from me by email sometime in the next week or so with the website information for you to register to get up to 2 tickets a person. Entry is free for that evening with the ticket. You just have to pick it up when you arrive here at the Science Centre. And the only charge is $5 for the parking, because it is a revenue event for the Science Centre. The other 200 tickets are being sold to the general public. So again, please make sure that you register for that early so that we can make sure that we use up our allotment of tickets. But that should be a really interesting evening. After Professor Weiss does his talk, then there's about a half-hour conversation that goes on after that, and Sarah Seeger is going to be the moderator for that conversation. So it should be a really interesting evening. Okay, solar observing. Our next session is this coming Saturday. Maybe. The last forecast I heard was lots of rain. So we'll have to watch out for that. Sean, as usual, will be the person who gives the go or no-go decision on that, and the backup date is a week after that, when we'll be knee-deep in snow or something like that, maybe. Who knows? But in any case, that'll be out on the telescape if we do get a clear event. Okay, our monthly dark sky star party will be the first clear night of the week of November the 5th at Long Sault Conservation Area. And again, the go or no-go will be made in the afternoon each of those days until we either run out of time or we actually have a program. Similarly, the following week we have the City Star Party at Bayview Village Park, and again, first clear night of that week. Remind you that the EC Carr Astronomical Observatory is our dark sky facility, a couple of hours drive northwest of here, and you just need to book your reservation online using your RASC member ID and password, and you can go up there to use the facility. And remember, we do have on the weekend on-site supervisors most weekends, which will allow you to use some of the facilities. Although that's rapidly running out now, we're going to winter mode very, very shortly, which means that you're basically on your own. No supervised weekends. For those of you who are closer into town, you can perhaps take advantage of our telescope loan program. And we've got at least one of our, George is here. Anybody else? No. So we've got one of our managers here this evening. So if you're interested, please see George about getting access to the telescopes. Okay, and finally, an invitation to join us at the meeting after the meeting at the Granite Brew Pub down at Mount Pleasant and Eglinton. And hopefully we'll see a few of you there. And that's it for tonight. We will see you in a couple of weeks for the next meeting. Thanks very much. Good night.